Hi, I'm Dr. T and welcome to my office. So today I'd like to talk about vacuums and addressing misconceptions about them. Of course, in this case, I'm not talking about sweepers or other devices that suck dirt off your floor. Instead, what I'm referring to is empty space. Literally nothing. The absence of air or other assorted gases. And of course, we can create these on Earth. You take a container, you suck the air out. Now, in this case, you're probably not getting 100% of all the gases out of it, but you can get pretty close. And this can be quite useful for us. There are certain types of chemistry that don't quite get along with air too well, and thus it's nice to do those under vacuum. You can draw off certain substances, or in some experiments where you need, say, a beam of electrons, an electron microscope, well, the air would get in the way. So if you have any air there, it's going to mess up your experiment. So yeah, we can pump out the air, we get ourselves a vacuum. Now, vacuums do and don't do a couple of rather important features. One of the things they don't do is they don't transmit sound. Sound needs a medium to go through. Vacuum is empty space. No medium. So while you can transmit light through a vacuum, sound, it's got nothing to go through, so it's not going. Now, of course, if you hop in a nice spacecraft, maybe one of SpaceX's Dragon capsules, you launch and you can get up into Earth orbit, and you're in a nice vacuum. Now, a couple quick points here. If you're actually fairly low on your Earth orbit, you actually still have a little bit of air, and that actually is important for low Earth orbit satellites. If there's air, as you travel, there is air resistance, and those will slow down and fall back to Earth over time. But if you go high enough up, you're completely out of the atmosphere, and as such, hey, no air resistance, you can just kind of keep going. And a lot of our geostationary satellites will just kind of stay there for very long periods of time, leading to, issues with space junk and the like, but that's a different topic. Now, I do need to point out, though, that once you're in space, you are in a vacuum, but just because you're in a vacuum doesn't mean there's no gravity. Vacuums are absences of air, not absences of gravity. And this is actually a fairly common misconception that's fueled from the fact that when you look at astronauts in space, they're weightless. But they're weightless not because there's no gravity. They are being pulled on by gravity. They are actually falling towards the Earth. They are in what's known as free fall. What's missing is the normal force. That is the thing you're standing on. So right now I'm sitting in a chair, and that chair is pushing back up on me as much as I'm pushing down on it. It's pushing back up on me is the normal force. If I don't have a normal force, I fall towards the Earth. And, well, my fall wouldn't last very long. I'd be hitting the Earth pretty quickly. If you are going fast enough around the Earth, or really any large, spherical-ish thing that has lots of gravity, then you can enter orbit. So orbit, we think of as a location, but it's not. It's actually more of a velocity. So the idea here is that if you are traveling forward really quickly, and the thing you are traveling around, the planet you're on or over, is round, then as you go forward, if you're moving forward enough, as you fall down, the curvature of the Earth, or whatever else you happen to be orbiting, like the moon or Saturn or the sun or whatnot, arcs away as quickly as you fall down. And you can get going in this nice circle where you're effectively falling in a circle. If there's no air resistance, then you're not slowing down either, so you can just continuously fall around the Earth constantly. You have to be going ludicrously fast, though. Far faster than what you would reasonably ever want to think about doing when you were actually in the atmosphere, because all that atmospheric drag. But you can definitely do this. It feels like you don't have gravity affecting you, but you do. That's what's holding you in your orbit. That's why you're not just flying off into space aimlessly. It's because of that gravity. Now, a couple quick points, though. As educators, we like to simplify things, and sometimes talking about motion, etc., well, that air resistance gets really annoying, because it's actually a really complicated thing. It depends on the density of your object, the shape of your object, the speed in which it's traveling, the type of air in which you've got. And heaven help you if there's actually like a breeze or something, just to make things even more complicated. So quite often we'll talk about examples of what happens if I toss a ball on the moon. It travels up, it falls down, and we're ignoring air resistance. We like to simplify things because it's easier to understand something simply and then learn its complexities than it is to try and take the whole thing full complexities, full face, right to start with. That typically just kind of overwhelms people, and learning doesn't happen when you're overwhelmed. But one of the things to remember is just because it looks like the astronauts are floating in space completely unaffected by gravity, it's not the case. They are definitely affected by gravity. They don't feel it because there's nothing actually holding them up, but they are still falling towards the Earth. They're just falling around the Earth because they're moving really, really, really fast. So with that said, have a wonderful day, and I'll see you in later videos.